Hello, welcome to another video of heuristic algorithms. In this video I'm going to discuss the Newton method and how it could be implemented, and other methods that could be used to maximize or obtain the maximum of a function, of a nonlinear function. First, let's consider a couple of functions. We have y equals minus 5x squared plus 4x plus 12, and the other function y equals minus 10x to the 4 plus 8x cubed plus 5x squared plus 4x plus 12. And I have prepared this spreadsheet that contains a couple graphs. In the case of the more simple function, if y is negative 5x squared plus 4x plus 12, then the derivative is, I have a typo here, the derivative is negative 10 plus x4. The computation is correct, and it's readily visible that if we set the derivative equal to 0 for this equation, x would be, when y equals 0, x would have to be 4 over 10, that's 0.4, that's the value here, which is, as we expected, the value at which the original function y it reaches the maximum. And in general, the challenge is to find the maximum, and a way to find the maximum is to find the point where the derivative is equal to 0. Here we have the more complex situation. We are also interested in finding where the maximum is for y equals, and we have this long expression, and we can compute the derivative of y as y prime, and we would obtain negative 40x cubed plus 24x, here I have another typo, x squared, x squared plus 10x plus 4, and the derivative is the function that we have here in red, as we have indicated here, y2 prime, and the value is 0 at about 0.97 or 0.98 around, and that's where we obtain the maximum value for the original function y, or in this case y2. So there are many ways to try to solve this. One way, as described in our textbook, is to make partitions. If we know that there is a line that the derivative here, one side is positive and the other side is negative, then we would expect at some point it crosses in between, and we partition this area time and time again until we find where the point or the line, the function, in this case the derivative, crosses the horizontal axis, and that's where we would obtain the maximum. In our book there is also a method that is more efficient, and it's the Newton method. It's very practical because we don't need 2 points to start with. We only require 1 point, and by virtue of computing the derivatives, we can obtain the maximum. The way that the Newton method works is based on the derivative, as I mentioned, and of course we know that the derivative of function is the differential of y over the differential of x, and when this differential of x is tends to be 0. And then what this is computing is, what we're going to try to do is, say for instance we start this computation at this point here, then the derivative of the function at that particular point intersects the horizontal axis at x1. So at that point we recompute the derivative, and that takes us to another intersection of such derivative, or the projection of that derivative as a straight line into the horizontal axis at x2, and so on and so forth. And that's how we reach the value of the root. Now we're trying to maximize or minimize what the function that we need to find the root of is when the derivative is equal to 0. So actually we would need to compute the second derivative, but more on that in a moment. So this is a mathematical demonstration of why we can use the Newton method, or why the method works as it is. And basically what we're trying to find is the next x as a function of the previous results, and this is what we obtain here. When we simplify this arithmetic procedure, we have the next x that we have will be the previous that we have minus the computation of the function that we're interested in obtaining the root over the derivative of that function. Now we are not, if we try to maximize or minimize a function, the function that we need the root of is the first derivative of the function to be maximized, because at the maximum or the minimum the derivative is equal to 0. So this translates in the fact that for a function that wants to be maximized, in order to maximize it, we would have to use as a function here in the numerator, we would use f prime, the first derivative, and in the denominator we would use f double prime, which would be the second derivative. And that's how I have implemented the method in the code in Visual Basic. So how does that look? Let's first start with the simplest of the cases, which is well, not the simplest, but one of the ones that I have implemented, which is the function that I originally had as negative 10x squared plus 8x cubed, etc. The first derivative fortunately can be readily computable regardless of the function that I have, if I have a function defined. And all I have to do is compute the function as the function of x plus h minus the function of x, and divide those two by h, because by the definition of what the derivative is, this would be the differential of the function divided by the differential of x, and as long as the differential of x, in this case h, is very small, then we would obtain a derivative. And by doing a little bit of algebra, we can obtain that the second derivative is the function of x plus 2 times h now, minus 2 times that function of x plus h plus f1, or that function evaluated at x, and all that divided now by, not by h, but by h squared. All I'm doing is really applying again this formula, but now the original value would be the complete formula as the function to be computed the derivative, and by virtue of doing this twice we obtain this function. And that's all you need to do really, because now I can come here and define an h, which is the size of my differential in x and my starting point, and I repeat that process for the Newton method several times, and I set up a criteria how many times I'm going to do it. I'm going to do it as long as that derivative is larger than the value of epsilon, and I set an epsilon close to 0. So in such a way that if the derivative eventually reaches a value that's very close to zero, then that means that the original function that I get, that I was working on, is a maximum or a minimum, and all that is just implemented in this simple equation, which is the new x is the previous x minus the first derivative over the second derivative. Again, because we're trying to find the root of the first derivative and therefore maximizing the original function. The rest of the code is just allows me to print out my results into the spreadsheet that I had. And the beauty of computing the numerical derivation in this way is that I don't need to change a lot my program to change different functions, because in this area here with the function of f of 1x, I can just decide which function I want to maximize, and I can just change that function, and the rest of the program does not need to be changed because the derivatives are not analytical but numerical. So every time that the function is changed and the new derivative needs to be computed, the new derivative is computed based on a calling of the function that I just specified. So the only change that I need to do for different code is here, and let's run it. As I said, I implemented this in a macro. These are my outputs. This is my value for the solution, or the value of x. This is the maximum value that I obtain when I evaluate the function, and this is my derivative of f, and this is my second derivative of f. And for this problem, I execute the code, and we see that the value that we should get is 0.96 5975. The maximum value that we would obtain is 19.03. The derivative there, as we expect, is close to 0, and the second derivative is 55. Compare those data to these ones that I managed to obtain using the solver in Excel, the package that we got. The value is pretty much the same, and the maximum value is pretty much the same. So this is a very efficient way to do it, very easy to code. Let's go really fast to make some changes, maybe compute the maximum value for the next function. And as we expected, as we mentioned before, the maximum value is at 0.4, that's 4 over 10. The maximum value is achieved at 12.8, or the maximum value of the function is 12.8, and again the derivative is 0 or close to 0. And I can do this for other type of functions that are more difficult to solve analytically. Not extremely difficult, but you would need to remember the derivative of logarithms and things like that. In this case, we don't even need to code that. All I'm changing is the function and re-execute the code. And for the function logarithm of x minus x squared, the maximum is at 1 over square root of 2, and we obtain the maximum or a minimum, and the value of the derivative again is very close to 0. Finally, I have a more common function that's sine of x divided by 2. And again, you don't need to memorize all those derivatives with respect to for trigonometric functions, etc. or any combinations. Here I could in theory combine polynomials with logarithms with trigonometric functions, and it should work fine for the most part. And we have that the value of where we obtain the maximum of 5 times the sine of x divided by 2 is precisely pi. So again, and the maximum value naturally is going to be 5 times 1, that is 5, and the derivative is 0. And the second derivative is there. There are some limitations to this code. Not everything is perfect and smooth, because for instance, let's work with this problem with the original derivative. If I run the code, I obtain the solutions that I want. But if I try to increase the precision of my derivative by adding more digits here, and I try to run the code, I'm going to have an error, a division by 0, because the second derivative is not being able to compute. The reason for that is because when we are computing with these computers and you make your own code, there is some limitation on the number of digits that the computer is going to take into consideration, and if these numbers are very small, then the computer just round it up, and if it's very small, it's going to round it to 0, and you're going to find problems of making divisions by 0, or in this case these numbers are not being able to pick the difference in y's because it's so tiny. The computer just says, you know, that's 0. So when it's coming here to compute the second derivative, the second derivative appears to be 0, because there is this difference is very tiny, and we run into numerical problems. But other than that, this method is very efficient for most engineering applications of maximizing nonlinear functions.